So in video 4, what we're going to do is look at the impact of multiplying the input variable for the sine or the cosine function by some positive scalar b. So we're going to start by taking a look at it in GeoGebra. And what I have graphed for you on the screen is the Toolbox function cosine of x. So it does exactly what it's been doing for us. It starts at a high point of 1, goes to 0 at 90 degrees or pi over 2 radians. At pi, we're down to -1. At 3 pi over 2 or 270 degrees, we're at 0. And at 2 pi radians or 360 degrees, we're back to where we started at. So the period of the Toolbox function cosine of x is 360 degrees. And what we want to look at is what happens when you take, for example, and multiply that input variable x by a number like 3 times x. Well, we're multiplying the input variable by a number. So the impact to the function should be an impact that happens on the horizontal or input axis. Things that we do to the input variable impact the horizontal nature of the graph that we're working with. And what's going to happen is this is actually going to compress the graph by a factor of 3. The idea is that multiplying an input variable by 3 makes the input variables 3 times bigger. It should make everything that happens to the graph happen 3 times faster than what is usual. So when I take and graph the cosine of 3x, this is what it looks like right here. And what you'll see is it's 3 times faster than the Toolbox function cosine of x. It starts at its high point and winds up back at its high point again once. Starts at the high point, winds up back at the high point twice, starts at the high point, winds up at the high point 3 times in the time it takes the Toolbox function to start at its high point and get back to its high point 1 time. The function cosine of 3x is 3 times faster than the Toolbox function cosine of x. And in fact, what we could do, if I can get the eraser and erase part of this, is we could focus on one cycle of the cosine of 3x. How long does it take to start at its high point and get back to its high point 1 time? How fast does that happen, or when does that happen? Because that's going to be the period of this function. This function has a period. The period of the cosine function is 2 pi radians or 360 degrees. That is the angular distance through which the input variable needs to go to get from the high point back to the high point. Our function's 3 times faster. So notice the question that we can ask, let's say we want to work in degrees, 360 degrees. What we can ask is, when does 3 times x, when does the input equal 360 degrees? Because that, when the input equals 360 degrees, that means we've gone around the unit circle 1 time. We started here, 360 is 1 time around, and we divide this by 3 on both sides. We see that we get 120 degrees. So this point right here on the graph, this should be 120 degrees, because 120 is the number I plug in for x to get 360, or once around the unit circle. If I were working in radians, I would ask the same question. I would say, if I want to label this as 2 pi, which is how we have the input axis labeled as 2 pi, just ask the question, when does 3x equal 2 pi? Well, hey, divide both sides by 3, and we discover that 3x will equal 2 pi when x is equal to 2 pi over 3. You plug cosine, we've got 3 times x, but when we plug 2 pi over 3 into 3x, we get 2 pi, or once around the unit circle. So this tick mark would also correspond to 2 pi over 3 radians. We would say that's the period of the function cosine of 3x. So if we turn the cosine of 3x off for a minute and erase some of this garbage here, if I can get the eraser to turn on for me, there we go. So erase the stuff for the cosine of 3x. We could look at what happens to the function cosine of 1/2 x. So here's the cosine of 1/2 x. Let's graph him. There he is. And we'll get some of this other stuff out of the way. Turn the pin back on if I can. There we go. So the cosine of 1/2 x, whose graph I have here, I'm multiplying the input variables by 1/2. I'm halving them. So it should take me twice as long to move through one full period. So notice I start at the high point here, and I don't wind up back at the high point until way over here. Having the input variables made it take twice as long for things to happen. In fact, notice I have to plug in 4 pi. Plug 4 pi in here. Cosine of 1/2 times 4 pi. 1/2 of 4 pi is the cosine of 2 pi. Ooh, 2 pi radians happens when we plug 4 pi in. We make it once around the unit circle. So the period is 4 pi for this function. In fact, we could solve for the period by saying, hey, I have the cosine of 1/2 x. When will 1/2 x equal 2 pi, which is one trip around the unit circle? And you solve it for x. You say, hey, multiply both sides by 2. 4 pi is when I will make it around the unit circle one time, because plugging 4 pi in for x generates 2 pi, or one trip around the unit circle. So let's sneak back into PowerPoint and summarize this. Turn presentation mode on and advance forward a slide if I can. So in generic world, where we don't know what b is, we just say, hey, b is some real number and I want b to be greater than 0. B can be negative and it causes a reflection in the y-axis, but the symmetry of the sine and the cosine function are such that it's never really necessary to let b be negative. So I'm going to focus on b being a positive scalar. So let's say you're going to graph the sine of b theta. Here's how you do it. You say, hey, the sine function is the toolbox function. I don't have a horizontal or vertical translation. So what does the sine function usually look like? And you go ahead and you graph the sine function how it normally looks. We know that it starts at the origin. It goes up to its high point. The toolbox function, this high point would be 1. It comes back to its midline, or the input axis. And then it swings down to its low point and back to the input axis. So that would be one period. And usually we're going from -1 to 1. And in this case, if we don't have anything in front of the sine function, we'll still be going from -1 to 1. Usually this is 360 degrees, but that won't be the case now, because for my function f of theta, and I have theta here, my input variable is b times theta, and what I need to know is, when will b times theta equal 2 pi? This is something I need to know, because 2 pi is one trip around the unit circle. So when b times theta equals 2 pi, I will have done one period, or one trip around the unit circle. And to get theta by itself, I see that I just need to multiply both sides by 1 over b, or divide both sides by b. So I get 2 pi over b. So this tick mark here, instead of being 2 pi radians, is going to be 2 pi over b radians. And I know that I break my function into force, high point, theta axis, intercept, low point, theta axis, intercept. I break it into 1, 2, 3, 4 equally sized regions. So what I do is I take 2 pi over b, and I just multiply it times a fourth to get this first tick mark. This will be a fourth the length of the entire interval. So it's going to wind up being 2 pi over 4b, which simplifies to pi over 2b. So here I have pi over 2 times b, 1 pi over 2 times b, 2 pi over 2 times b, 3 pi over 2 times b, and this here will be 4 pi over 2 times b, which simplifies to 2 pi over b, which is how I labeled that tick mark. If I am working in degree world, so let's do the cosine function working in degree world. So right here, we'll graph the cosine function. So I called my function f of theta, so that will be my output axis. I've got thetas going in on the input axis, and the cosine function usually starts at the high point, goes to the theta axis intercept, down to its low point, up to the theta axis intercept, up to its high point again, and usually this happens in 360 degrees, but it isn't going to happen in 360 degrees anymore, and there's no scalar in front of the cosine function right here. This is just, we're just graphing f of theta equals cos b theta. So it's still going to go from 1 to a low point at -1. So this isn't going to be a 360. What we have to ask is, when will b times theta equal 360? Because for that value of theta, we will have gone once around the unit circle. Divide both sides by b to solve for theta. We see that theta will equal 360 degrees over b. So instead of 360 here, this is going to be 360 degrees over b. And we break our interval, our period, we break it into fourths. Here's a fourth of it, here's a fourth of it, here's a fourth of it, here's the final fourth. So to get the first tick mark right here, I take 1/4 times 360 degrees over b, and a fourth of 360 is just going to be 90 degrees over b. So this first tick mark is going to be 90 over b, 2 times 90 over b, 3 times 90 over b, 4 times 90 over b. So let's do one as a concrete example. So here I have b equaling 2. It's the cosine function. There's no scalar in front of it to change the amplitude. So it's going to go from -1 to 1. Just draw what the toolbox function looks like. The toolbox function starts at its high point, goes to the input axis, drops to its low point, goes back to the input axis, returns to its highest point. And we're going to come up with a tick mark here. We know that the function goes from 1 to -1 because there's no multiplier out here to change the amplitude. And then we just have to figure out what number goes right here. And to do that, we say, hey, the input is 2b. Usually this is 360 degrees if we want to work in degree world. And you should label this axis. Here's my f of t, and I'm using t for my variable name, so this is the t-axis. So just ask the question, when will 2 times t equal, if we're in degree world, when will it equal 360 degrees? Divide both sides by 2 to get t by itself. We see that when we plug in 180 degrees for t, we get 360 degrees, or once around the unit circle. So this is going to be 180 degrees here. And our interval from 0 to 180 is going to be broken into fourths. So we take 1/4 of 180, and 4 is going to go into 18. We're going to get it's going to go in there 4 times, which would be 60. It'll leave us with 20 more degrees, and 4 will go into 20 degrees 5 times. So 1/4 of 180 degrees is 45 degrees. So these tick marks are at the 45 degree mark for the first one. 2 times 45 degrees is 90 degrees. 3 times 45 degrees is going to be 135 degrees, and 4 times 45 degrees is 180 degrees. So there is one period of the graph of this cosine function. We'll do one more example with the sine. So something that looks a little more complicated but really isn't. We have a multiplier on the input variable, which is going to cause a horizontal stretch or compression of our function. We don't have anything being multiplied on the outside of the sine function, so the amplitude is still going to go from -1 to 1. Again, start off by drawing what does the toolbox function look like. Well, the toolbox function sine of theta would just start at the origin, go up to its high point, would go down to the axis, the input axis, would drop down to its lowest point, would come back to the input axis. There's one period. Everything that has happened has just happened. The amplitude is still going to be 1, so our function is going to be going from -1 to 1. This is the t-axis because t is the name of my input variable. This is the f of t axis, my output axis, and we need to figure out what number needs to go right here. The pi that I see here tells me that a natural way to measure things would be in radians. So I'm going to take the input to the function. The input to the function is 4 pi over 3 times t, and I'm going to ask the question, when does this input equal 2 pi, which is one trip around the unit circle? It's one period, or one trip around the unit circle. And to get t by itself, I'm just going to multiply by the reciprocal of the coefficient on t. So I'm going to multiply by 3 over 4 pi, because when we multiply by a reciprocal, we get a 1. 1 times 1 is 1. So I'm multiplying by the reciprocal of the coefficient, 3 over 4 pi, and then I can simplify things. So this is going to be what? 2 is going to go in here twice, and the pi's are actually going to cancel and give us a 1. Pi divided by pi is 1. So we get 1 times 3 is 3 over 2. So instead of 2 pi, this is just going to be 3 halves. And just for emphasis, notice what happens if we take 3 halves and we plug it in for t. We plug 3 halves in here. What does this simplify to? Boom, boom, boom. Ka-ching, 2 pi. 2 pi radians are once around the unit circle, so one full period. And then we know that we're broken into fourths. So to get this first tick mark, I need to take a fourth of 3 halves, which is just 3/8, and this is going to be 3/8 times 1. 3/8 times 2 is 6/8. 3/8 times 3 is 9/8, and this is going to be 3/8 times 4 is, this is 12/8 right here if I don't simplify it to 3 halves. I know that we're always taught to simplify fractions. I think sometimes when you're working with graphing these trig functions, there is some glory in leaving a common denominator sometimes. So 3 times 1, 3 times 2, 3 times 3, 3 times 4 is 12 over 8. This actually isn't a bad way to label the axis, in my opinion.